got a question from somebody on YouTube. They were they were kind of complaining that I don't live stream my classes on YouTube, and I was just thinking, man, oh man, isn't there better stuff to be watching than live fluid mechanics videos? I can see maybe if you're enrolled in the class, or if you have a specific question on a homework problem, looking something up, but I don't know if I'll be live streaming this stuff on YouTube anytime soon. Homework 5 is due on Tuesday of next week. We're going to be talking about acceleration and how that can determine pressure changes. And so we're going to work through a couple of examples that will play into homework 5. And of course, remember that the flow classification and the visualization problems that we looked at on Tuesday, that's also in homework 5. So go ahead and get started on that. We looked at a nozzle in class last time when we were talking about different flow types. And this nozzle is associated with non-uniform flow. Remember that the 3 different flow classification categories that we discussed in class on Tuesday was, first of all, laminar versus turbulent. There was also steady versus unsteady, which is all about whether or not flow conditions are changing with respect to time. This, though, is non-uniform flow. And what non-uniform flow is, it's where the flow velocity is changing with respect to position. And so since the diameter of this nozzle is decreasing, what it's doing is it's forcing the same flow rate through a smaller cross-sectional area. And so, you know, when 1 liter of water enters the entrance of this nozzle, that pushes 1 liter of water out through the exit of the nozzle. Water is nearly incompressible, and so if 1 liter comes in, 1 liter has to go out. But the difference between the inlet and the outlet for this nozzle is that the inlet has a larger diameter and the outlet has a smaller diameter. And so in this case, what we see is that the water comes in at a velocity of 10 meters per second and exits at a velocity of 20 meters per second. So convective acceleration is what causes non-uniform flow. And what we're going to do is go through the process of finding out how much convective acceleration there is at the midpoint of this nozzle. This problem statement is saying that the nozzle itself is ½ a meter long. And so L, the length of the nozzle, is ½ a meter. And we want to know in the middle here where the walls of the pipe are coming together, that's what's causing the acceleration in the fluid, is that the diameter is changing. And we have this equation over here on the right that's describing how the velocity varies inside of this nozzle. And so U0 is the entrance velocity of 10 meters per second. So let's just first of all try and think about what is this equation telling us. It's telling us that when you're a certain distance into the nozzle, how much the velocity is at that location. So for example, when we're all the way through the nozzle, so at that location, x is equal to L. So when we are ½ a meter away from the entrance, then x and L are both 0.5. So they cancel each other out. And so then what's in the denominator here is 1 minus 0.5. And so if our initial velocity is 10 meters per second, then the exit velocity would be 10 meters per second divided by 0.5. And so it's 20. And so this equation is plausible based on the image that we have to the left that tells us the outlet velocity is double that. So this equation just tells us, you know, for example, if you're halfway in, then what's the velocity? So, you know, we can crunch that number real quick here. If you'll get out your calculator, and I'll get out mine. So if we are at x is 0.25, so in a little scratch piece of paper, hopefully by the side of the notes, what you can do is let's find the velocity at x equals 0.25 and L equals 0.5. So if you substitute that in, it's going to be 10 meters per second divided by 1 minus 0.5 times 0.25 divided by 0.5. And so the velocity in the middle hopefully should be somewhere between 10 and 20. If it's not between 10 and 20, then things have gone horribly wrong. So 0.5, 0.25. Anybody running these numbers as well? What I got is 13.3 meters per second. Let me just double check that. Courtney, thank you for verifying that. All right. So that makes sense, right? The water is speeding up. As it goes from the entrance to the exit, it's speeding up. So in the middle, it's going to be between 10 and 20. So this equation will tell us at any location what's the velocity. Now here is the equation for convective acceleration. When you took physics, when you thought about acceleration, probably what you thought of was a change in velocity with respect to a change in time. That's local acceleration. What we're talking about here is something different. We're talking about the kind of acceleration that's associated with non-uniform flow. We're not talking about the kind of acceleration that's related to unsteady conditions, but this is for non-uniform. And so the formula for acceleration that's convective acceleration is a little bit different. And you can see that the convective acceleration is the velocity at a certain point multiplied by du dx. So we're going to actually dust off our calculus here for a minute, because what we have is an equation for velocity, and we have to take the derivative of that equation with respect to x. And so at a certain location, we want to multiply the velocity at that location, u, with du dx. All right. So let me open up the solution for this one, because it may have been a while since you used the chain rule in calculus, and I have a little summary for the chain rule that I'd like to share with you. Almost there. All right. So what we're doing is, this is asking, find the convective acceleration at x is 0.25. And so the acceleration, by the way, isn't the same everywhere in here. Think about where the walls of the pipe are relatively parallel to each other. There's no acceleration. If the pipe diameter isn't decreasing at a certain spot, there's no acceleration. The acceleration is the highest when the pipe walls are converging at the fastest rate. And so just visually, if you're looking at this, it looks like the pipe walls are relatively parallel here. So there isn't going to be much acceleration at the beginning or at the end, but it's where the pipe wall is converging the most that the acceleration occurs. And so what we got to do is, if we want to find out here in the middle, find the acceleration at x is 0.25, meaning in the middle of the nozzle, we're going to find what's the velocity at that location, which we just did. It was 13.3 meters per second. And now we have to have du dx. And so we're going to take the derivative of this equation. So the chain rule. Here's what we're going to do. Here's the formula for convective acceleration. It's the velocity at a location multiplied by du dx. And so here is u. We have to take the derivative of u with respect to x. Now we can't do it in a single step. What we have to do is assign a pseudo variable, because if you look our unknown down there in the denominator, so the chain rule says that if you want to find du dx, then that's the same as du dm multiplied by dm dx. And what we're going to do is we're going to assign the entirety of the denominator. We're just going to call that m. And so I'm going to take the derivative of our velocity equation with respect to m and then dm dx. So it's just, we're going to make a temporary substitution. I'm going to let m be what's in the denominator of our velocity equation. So if we rearrange what is the equation for velocity, what we're saying is the velocity is the initial velocity divided by our new pseudo variable m. And the other way that we can express that, of course, is if you're dividing by m, that's the same thing as m to the minus 1 power. So this is u. So what's du dm? So if you have m to the minus 1 power and you're taking the derivative of that, you can see now it's going to, if we do this substitution, we're saying that du dm multiplied by dm dx. So du dx is this first part with respect to m, and then this same substitution dm, and here is, that is what m is with respect to x. So now when we apply the chain rule, if our pseudo variable m was at the minus 1 power, it now becomes to the minus 2 power, and the exponent comes down in front. And so the derivative, this was positive, but we move the exponent in front of the variable, so the minus 1 goes down there, and now it's to the minus 2 power. Now that we've taken the derivative with respect to m. And then for this equation, we want to take the derivative with respect to x. So it was x to the first power, but now it's x to the 0 power. And so x to the 0 power is the same as just 1. So what that leaves us with in the second part of the chain is 0.5 minus, 0.5 divided by L. And this constant goes away when we're doing the derivative. So it's gone entirely. So now what we're going to do is substitute back in. We remember what m stands for. We defined it up here, and now we're refreshing our memory that we don't want to have this equation in terms of m and L, and so we're going to substitute m back into its original form. And so du dx is this. So down in the denominator, the m to the minus 2 power is the same as saying that you're dividing by m squared. So it's minus 1 u naught, the initial velocity, divided by m squared. And so I've resubstituted m back in. And then the second half of the chain here is just times minus 0.5 divided by L. And so I combine those two pieces together and then substitute in for the known x value of 0.25 and the known length. So u du dx, u is the initial velocity. So you can see that when we make the substitutions that our convective acceleration at the middle of the nozzle is 237 meters per second squared. Now, it's probably been a while since you did this, and so I think there's really only one homework problem where you're going to need to apply the chain rule, if I remember correctly. Unfortunately, we don't have enough opportunities to apply calculus in the fluid mechanics course. It's just occasionally, but here's one of them. And what we were doing is we were trying to find out what is the acceleration that is causing non-uniform flow. And so Acceleration has the same units. I have to point this out. Remember, I was contrasting the difference between local acceleration and convective. Local acceleration is associated with unsteady flow, and that's where the velocity is increasing over time. But here the velocity has no change with respect to time, it's changing with respect to position. But it still has the same units, meters per second squared. And it's kind of interesting that a convective acceleration, when it's not changing with respect to time, still has time units describing it. So that's how quickly the velocity is changing at that particular location. So the key thing to remember is that you have to take the derivative of the velocity function with respect to x and then multiply it by the velocity at a certain location. Any questions? Is there a certain part of that illustration that anybody needs to see before we move on? All right. Will the velocity function change with the shape of the pipe? Absolutely. That's a good question, and it definitely will. You know, it could be that you have a linear slope, you know, that maybe the pipe is bell-shaped. But yeah, it's not like every nozzle would have that same function. It would change. Okay. So that is convective acceleration. Now, just to review, steady flow is where velocity is constant with respect to time. Uniform flow is the velocity is constant with respect to position. Local acceleration causes unsteady flow, and it's where the velocity is changing over time. And so the formula for local acceleration is some change in velocity with respect to time. Convective, which we've just been talking about, is what causes non-uniform flow, and the formula for convective acceleration is the velocity at a certain location multiplied by the gradient with which the velocity is changing with respect to position. So the dv dx, or here, you know, s is our position term, and so the change in velocity with respect to position. These two different types of acceleration both cause a change in fluid pressure. Until now, the formula that you've used to describe how the pressure of water is changing was just the hydrostatic equation. That's the only formula that you've used so far to tell you how pressure of water is changing. But as the name implies, the hydrostatic equation really is only suitable if the water isn't moving. So if there's no velocity, no acceleration, then the hydrostatic equation is great. But when the water starts to move, the hydrostatic equation doesn't apply any longer. And so different types of acceleration, we're going to use equations that have been derived from those acceleration types to describe how the pressure is changing. Harrison asks, should you use V or U to represent velocity? And I don't really have a preference, and you know, the notes switch back and forth between the two. So whichever you prefer is fine. What we're going to talk about today is Euler's equation. There's a formula that tells you how you can determine a pressure change when fluid is experiencing a local acceleration. So Euler's equation tells you what is the pressure change for a fluid that has unsteady flow. Now, here is another way of just illustrating steady versus unsteady, uniform versus non-uniform. And so you can have steady flow that is uniform. And steady uniform flow is pretty easy to calculate because there's no change in the velocity with respect to position, and there's no change over time. Unsteady flow that is uniform would be, this is a pipe where the flow in and the flow out are equal. And so the reason why we have this straight wall pipe is just to illustrate that there's no change in velocity with respect to position. But if it's unsteady, then that could mean that an hour from now, the velocity in and the velocity out are greater than they are at this particular instant in time. Non-uniform flow, instead of the parallel pipe, here I have a nozzle, just to illustrate that the flow velocity is changing with respect to position. So there is a change in velocity as it moves from left to right if the diameter is decreasing. But you can have steady non-uniform. So steady non-uniform means that over time the flow rate in and the flow rate out isn't changing from one moment to the next. But unsteady non-uniform would mean that over time maybe a valve is opening. And so if a valve is opening and it's increasing the flow rate through this nozzle, then that would mean that it's both unsteady and non-uniform. So I wanted to illustrate that there's a 2x2 matrix, that there can be each one of these possibilities. They all exist. Just because flow, for example, is steady doesn't necessarily mean that it is uniform or non-uniform, because you can have both cases. Now the Euler's equation is used when you have local acceleration. Local acceleration is the flow type that the velocity is changing with respect to time. And it tells you the relationship between pressure and fluid acceleration. And hydrostatic equation works great if the water isn't moving, but when the water is moving, then hydrostatic equation doesn't give you the full story. So just remember, as a summary, hydrostatic equation would tell you at a certain depth that you could have an increase in pressure, where at the top of the tank that's in contact with air, you'd expect the air and the water to both have zero pressure. You know, if we're talking in gauge terms and we're saying that the atmospheric pressure is the baseline, then the pressure is increasing as you go down through the fluid. Now Euler's equation says, what if this tank, instead of being stationary, think about what if it was being accelerated upwards, like in an elevator, for example. If you had an elevator that was constantly increasing its velocity up, you can kind of, in your mind, simulate what that would feel like to your body. If you are in an accelerating elevator, you'd feel more pressure on your feet. You know, your body would feel more heavy. Well, that same effect on the fluid would cause a greater pressure increase as you go down through the water than is predicted by the hydrostatic equation. So Euler's equation is the extension of hydrostatic, but it's for additional acceleration. So it's the gravitational effect, but then also if there's more acceleration on top of that, then Euler's equation can kick in and handle things. So for example, if this tank was accelerating up at 9.81 meters per second squared, and if delta H is 1 meter, then what would be the pressure at that location? This is not the way to always solve problems like this. I'll show you the full Euler's equation in just a moment. But if you have g is the normal acceleration, and then there's an additional g on top of it, then you could add up the accelerations, and if it's a vertical acceleration, then that would tell you that the pressure change is going to be 9.81 times 2, and then multiply that by the density of the fluid, and if this water, then that would be 1,000 kilograms per cubic meter. And the delta H is 1 meter. And so instead of the usual 9810 pascals that we'd see at a depth of 1 meter, it would double the pressure. So I think I have that calculation written out in my notes. Let me just bring it up on the screen for a moment here so that you see the calculations for that. Yeah, it's pretty simple here. So if if it's accelerating upward, then the g that applies is both gravitational acceleration and the additional 9.81 meters per second squared. And so it's accelerating upward, then the pressure increase is going to be double of what you'd ordinarily see. You know, the hydrostatic equation, we usually say it's delta H times gamma, right? But gamma is just the density of the fluid multiplied by an acceleration. And if the tank is accelerating upward, then it's the gravitational acceleration plus the acceleration of the tank itself. Now that's not Euler's equation, but it is giving you an idea of why there is more pressure at a certain depth. Alright, so Euler's equation comes from looking at an element of fluid. And let's say that this cylindrical shape that's shown is just representing a certain amount of a fluid. It may be water, it can be any fluid. But we're going to consider the local acceleration that this fluid element is experiencing. And because it's accelerating, there's going to be more pressure in one location than there is in another location. And this figure is, you can see down here with the axis, this is a three-dimensional drawing. We have the x direction, the y direction, and the z direction. And so this acceleration just is occurring in the L direction. So it's not along one of the axes, it's just in some direction the fluid is accelerating. And of course the weight of the water is downward, but as it's accelerating in this L direction, there's going to be an increase in pressure because of the acceleration that it's experiencing. And so the sorts of questions that we'd ask for this, if we were going to do a force balance, is we'd want to know what's the mass of the fluid element and how do the pressure forces change on the front of the cylinder compared to the back of the cylinder. And you know, what are the factors that cause the pressure change? It's partly going to be because of an elevation difference. It looks like the cylinder is somewhat vertically oriented, and so you know, this would be deeper in the water than this is. And so the Euler's equation that I'm about to show you, it already accounts for the hydrostatic effect, but it also accounts for the acceleration that occurs. So this is Euler's equation. And on an exam equation sheet, this is the form of it that I'll provide. But what you have to be able to do is know how to expand out this formula and apply it between points. What it's saying is that when you have acceleration in the L direction, that's over here on the right-hand side of the equation, fluid is accelerating along some path, then that acceleration is going to cause a change in the pressure plus gamma z. And you may remember from earlier in the semester that we talked about piezometric pressure. And that's what is inside of those parentheses, is pressure plus gamma z is piezometric pressure. And so local acceleration can change the fluid pressure, but it can also change the location of the water. I'm holding a water bottle in front of my webcam right now. And if I shake the bottle to the side really quickly, so if I accelerate it to the right, then what happens is that the water level goes at an angle. If the water was totally full to the top of the container and it couldn't slosh around, then the z wouldn't change. But if you think about a big bucket of water, and if you suddenly move to the side, then the liquid surface is going to change because of that acceleration. And what Euler's equation says is that an acceleration of fluid changes the sum of the pressure plus gamma z. And gamma z is the part of it that has to do with the elevation of the liquid. P is the pressure component of it. Now we apply this at 2 points that are a certain distance apart, and that's where this dl comes in. If we assume a linear variation between the piezometric pressure between 2 points, then it goes from becoming a partial differential equation to just saying that the change in piezometric pressure some distance delta x apart. If the acceleration is occurring in the x direction, for example, then the piezometric pressure increases in the opposite direction of acceleration. And so you'll notice that there's a minus sign in this formula. And the minus sign is to indicate that if your acceleration is to the right, then the pressure is going to be higher on the left side of any element of water. So if it's a tank of water and you start to accelerate the tank to the right, then the pressure increases in the opposite direction of that acceleration. And so we expand this out, assuming linear variation, from a partial differential to just saying it's a change in piezometric pressure over a distance. And then if we have 2 points in particular that we're interested in, then we can say that the pressure plus gamma z at location 2, so location 2 would be the location that's furthest to the right. If we're working in the x direction, so x is horizontal, then location 2 by definition and by custom is going to be the location that has the most x. So the piezometric pressure at location 2 minus the piezometric pressure at location 1. So the change in piezometric pressure can be calculated by how far apart they are, delta x, multiplied by the density of the fluid, multiplied by the acceleration. And then the minus sign, like I mentioned before, is just to indicate that the pressure will be greater in the opposite direction from the acceleration. So I'm sure this seems really abstract, but we'll make it real with a couple of examples in just a minute, and it'll, I hope, become instantly clear to you. But it's important to emphasize that 1 and 2 mean something specific. And one of the common mistakes that I see a lot in exams and homework problems is when students accidentally pick the wrong location as which one should be location 2 versus which of 2 potential points should be called location 1. And what we mean, our convention, is that if we're working in the x direction, then 2 is the point that's furthest to the right, having the most x. Or if this is a vertical acceleration, so if the acceleration is in the z direction, meaning up, then location 2 is of the 2 options that which has the most elevation. So I've sketched out here just to indicate that the most x is 2, the least x is 1, and of 2 points, whichever has the most vertical elevation is 2, and which has the least vertical elevation is location 1. So we only apply the Euler's equation in one direction at a time. You know, a tank of water could be simultaneously accelerating upward and also to the side. In a case like that, where there's 2 accelerations occurring simultaneously, then we will just apply Euler's equation in one of the directions at a time. Alright, so this is how we can start to get a feel for how this works. Think about if you had a truck that for some reason is carrying gasoline. It's maybe a tanker truck, taking gasoline to a station. And it's slowing down. Okay, so it's slowing down. That means that the acceleration is to the left. It says that it's slowing down at a rate of 3.05 meters per second squared. So it's driving forward, but it's slowing down, so the acceleration is to the left. And what we know is the dimensions of the truck. It's 6.1 meters long, and then 1.83 meters tall. And here at location T, the pressure is 0. It could be that there is some sort of a vent system that keeps the pressure at the headspace equal to 0. But the pressure here at location T is 0. So now think about it, first of all, before we start doing calculations, think conceptually. If the tank is slowing down, that means the acceleration is to the left, And I told you that pressure increases in the opposite direction of acceleration. So question 1 asks, what is the pressure at point A? And question 2 asks, where is the pressure the greatest? All right, so it's asking here at point A. So what we're going to do is apply the Euler's equation from location T to location A, because we know the elevation at both of them. They both are on the same vertical plane, and so, you know, if we said that the datum is the bottom of the truck, then Z for location T is 1.83, and the elevation for location A is the same. So they both have the same elevation, so the pressure isn't going to be changing because any one of them is lower in the fluid. The pressure is going to be higher at A than it is at T because the truck is slowing down. So think about the water is sloshing to the right as the truck is slowing down. All of that fluid wants to keep moving forward, but the truck is slowing down the fluid. And so there's more pressure at A than there is at T. And this Euler's equation is going to allow us to calculate what is the pressure at A. So let me remind you how we expand out Euler's equation. All right, let me copy this from this slide to the next, because what I'd like you to do is I'd like you to try out Euler's equation. So here is how we will apply it in the x direction. Okay. What do you know about what should be location 1 versus what should be location 2? Anybody willing to make a guess on that? Do we call A is that going to be 1 or 2? Gavin says 2, and he's right. Gavin, why is it that location A we're assigning as, you know, we're calling it 2? What's the rule that applies there? It's in the x direction. It has the most x. Yeah, it's furthest to the right. Good. Okay, so the way that you substitute in, we want to know P sub A. Okay, so P sub A. Now, ZA and ZT are equal. So if you substitute into this formula, P sub A is here, and that's an unknown. ZA, you can call that 1.83, but since ZT is at the same elevation, it's just going to cancel out. So we can eliminate the Z term right from the beginning. So PA minus PT is equal to minus delta X. Now delta X is how far apart they are in a horizontal distance, and you can see that the dimension says it's 6.1 meters. The density of the gasoline, you'll have to calculate that because you're only given the unit weight. I didn't yet give you directly the density, but I think you can probably figure out how to calculate the density of the gasoline, and then acceleration in X. Alright, so I'm going to pause for a moment and give you a chance to try and calculate what is the pressure here at location A. Show you that. All right. So we've got this tank of gasoline, and here is location 1, here is location 2. And we can determine the density of the gasoline by dividing the unit weight by G. And so this gasoline has a density of 672.8 kilograms per cubic meter. And the acceleration is negative 3.05 meters per second squared. And it's assumed that to the right is the positive direction in x. And since this truck is slowing down, that means that the acceleration is to the left. And so the minus sign is really important. We have to include that minus sign when we do the substitution into Euler's equation. And so here is Euler's equation, and you can see that I went through the process of assuming that we have a linear variation between the points in the piezometric pressure, and so rather than doing a partial differential, I'm just saying now it's a delta, and location 2 is A, and location 1 is T. So what I'm saying here with Euler's equation is I want to find the pressure at A, and you can see that I've already canceled out the Z sub A term because the elevation of location A is the same as the elevation of location T. And the minus sign that's here from 2 minus 1, I distribute that through. So it's the pressure at T minus gamma ZT, although the Z term cancels out anyway. But and then over here on the right hand side of the equation, it's minus delta x times the density times the acceleration in x. So when you cancel out all of the things that don't apply and rearrange, we're saying that the pressure at A is however much pressure there was at T minus delta x times the density times the acceleration in x. And so there's a minus sign here that's going to be canceled out by the minus sign in the acceleration. And that's why the pressure at location A is actually positive. It's because it starts at 0 and the pressure is increasing in the opposite direction as the acceleration. So the acceleration is to the left, the pressure is increasing to the right. So 12.5 kilopascals is the pressure at location A. So this acceleration that was happening is local acceleration. The truck's speed is slowing down. So over time, the velocity of that truck and its cargo, meaning the fluid, over time, the velocity of that gasoline is decreasing. And so that's a local acceleration that's applied in the x direction. Any questions about this first part of the example? All right, now in part 2, it's saying where in this truck is the pressure the greatest and what is the pressure at this point. Now it's a leading question if you think about the way that it's being asked, because what I've done is I've said here is location B, by the way. We're going to call this lower right hand corner of the truck B. So that's where the pressure is the greatest. If you go the furthest to the right that you can, that gets you up against this wall of the truck, and then as you go down through the fluid, the pressure is increasing there as well. And so the pressure at B is going to be even larger than the pressure at A was. So what we can do is we can apply Euler's equation from T to B. And that's what I do in the illustration of the solution here. Is I say, let's apply, the acceleration is still in the horizontal direction. And so location B is 2, and location 1 is, location T is 1. So the greatest pressure is at location B, and I'm saying T is the one that's furthest to the left, B is the one that's the furthest to the right. And so you can see I'm assuming that the bottom of the tank is my elevation datum. So I'm saying let's measure our elevation starting from the bottom of the tank, and that is why I've canceled out this Z sub B term, because it's 0. but the elevation at location T isn't going to be canceled out like I did in the previous example where the elevations was the same between them. So Z sub T is 1.83, Z sub B is 0. So what we're trying to find out is what is the pressure at the bottom right-hand side of the truck. So that is the pressure at location B. So I've rearranged Euler's equation to tell me that it's going to be the pressure at T, which is that's where it's vented and open to the atmosphere. So the pressure at B is partly going to be because of the elevation difference. And so this 12 kilopascal pressure change is partly that component of it is because it's lower in the water. It's at the bottom of the truck. And so Euler's equation automatically accounts for the hydrostatic effect. And it also accounts for the local acceleration that the fluid is experiencing. And so those two things together tell us that the pressure at the bottom of the truck on the right-hand side is 24.6 kilopascals. And so you can see this 12,517, that was the same as this from the previous example. Because from side to side, A and B are experiencing the same amount of pressure increase due to the local acceleration. It's just that B is lower down. And so it's got however much pressure there was at A, plus a little bit more because it's deeper in the fluid. So you don't have to kind of manually account for the hydrostatic effect. That's built into Euler's equation, as this demonstrates. This is the elevation component of the pressure change. This is the acceleration component of the pressure change. And overall, the pressure at location B, 24.6 kilopascals. All right, now let me just briefly pull up the homework assignment so that you can get a glance at that. Before I do, David asked the question, if the container wasn't a rectangle, would the greatest pressure be at the point furthest away from point T? Well, that depends on the shape. Like if it was triangular, or like if it was diamond shape, I don't know if it would be so straightforward, if it wasn't rectangular. You may have to calculate the pressure at a couple of different extremes. Like if it was really tall but only accelerating a little bit, then it could be that the greatest pressure is the one that's the lowest down. So I think I can't give you a general rule. It would depend on the shape, and it would also depend on how much acceleration it's experiencing. All right, let me bring the homework up on the screen. All right, so problem 4 is one where you are determining the effect of convective acceleration. So here I tell you what is convective acceleration, and I tell you the velocity at a certain location, and you have to solve for the velocity gradient. Velocity gradient is what we call du dx. So in the homework, boy, that's an easy, I can't believe I gave you such an easy homework problem. I'm asking you solve for du dx when you're given the convective acceleration and you're given the velocity itself. I'm ashamed at how easy that problem is. All right, so problems 5 and 6 are both Euler's problems. In problem 5, you have water flowing through a vertically oriented pipe, and you know the acceleration of the fluid, the pressure is given, the elevation is given, and so this you're just going to substitute into Euler's equation. And remember, A versus B, the way you know which one should be called 2 versus what should be called 1, the one that's higher up is the one that should be called 2. And by the way, while I'm thinking about it, you've seen Euler's equation expanded out in the x direction. It's the same thing when you expand Euler's equation out in the y direction, vertically. So this equation shows you that you just, instead of the delta x, you substitute in delta z. And instead of acceleration in the x direction, you have acceleration in z. And so on the homework, it tells you the acceleration is downward at 12.5 meters per second squared. So that's your acceleration in z, is minus 12.5. Excuse me. And then the elevations are given, the pressure at A is given, but the pressure at B is unknown. All right, and then problem 6, you're doing acceleration. It's accelerating 65 kilopascals at P and 183 kilopascals at point C, and you're having to calculate the distance m. And so the acceleration is in z, and the unknown is how far apart are these 2 points. And so again, you're going to be applying this formula. Since it's a vertical, this is the expansion of Euler's equation that will apply, and you're solving for delta z in that equation. All right, that's all the time that we have for today. Remember, if we look at the announcements one last time, that your homework assignment is due on Tuesday. That's not it. Here we go. Yeah. Tuesday, October 13th, your homework assignment is due, and if you have any questions on the exam, feel free to reach out, get in touch with me. That's it for today. Hope you have a good one. Bye-bye.